Hey guys, Dr. D here with another audio production tutorial online lesson. Today we're going to be talking about audio, physics of audio and sound and hearing. All right, let's do it. Okay, so first of all, one of the first concepts we want to understand is that sound is basically air particles vibrating around. We don't see sound. We can't really perceive it visually unless we document it and show some sort of graphical representation of it. But essentially what happens is when you put energy into an object, like I clap my hands together or I strike the string of a guitar, that energy is put into a material. The material vibrates, and it vibrates the air around it. And the air particles are basically constantly being smashed together and then bouncing apart, smashing together and bouncing apart. Much like in the illustration we see here, sound is air particles compressing together and spreading apart constantly, and we can represent that and understand that in a two-dimensional wave drawing that represents how far and the compression and rarefaction happens. The best way to think about this is like in a pond. You have a big still pond and you throw a rock into it. That energy is happening by the rock splashing into the surface of the water, causes a disturbance, and those waves form and slowly work their way away from the source of that energy disturbance. And that's a lot like what goes on in air particles with sound in a room, but in a three-dimensional space where the particles and the sound is traveling away in all directions, not just across a two-dimensional plane. Okay, so wave propagation. Propagation is a term for the movement of a wave. So when I splash that rock into that pond, the waves propagate. They move away from the source and they move out in all directions kind of equally in a certain manner. So propagation is the movement of the sound or the wave away from the source. Compression is the air particles that are being smashed together. When they're getting smashed together because the sound happened, the disturbance happened, the air is like freaking out, gets smashed together and spreads apart. The compression is the area where the molecules are compressed together, and rarefaction is the area when the particles are spread apart. So they kind of compress, they rarefact, compress, rarefact, compression, rarefaction, and the propagation is how that sort of occurs and slowly disperses and travels away in all directions. Propagation. Okay, cool. So when we sort of try to document this process, we have to think of it in a two-dimensional kind of way with a sound wave, and a wave is a diagram. And this diagram helps us kind of interpret the elements and the aspects of the sound. So when we kind of represent that compression rarefaction thing happening with a wave traveling from positive to negative, how quickly it goes or how far it goes, we have all these elements of the wave. One of the biggest ones is the amplitude. It is the power, the strength, the volume of a wave. However much energy you put into it, how hard you hit the guitar string or how quiet is going to reflect the amplitude of that wave. You can kind of see in the diagram, you have the measurement of that amplitude of this wave from the very bottom, the very trough of the wave, all the way to the very top. So it's measuring from the top to the bottom of the wave. Now, you can measure from the middle of the wave, from that center crossing line to the top. There's different types of amplitude measurements, but usually they're measured from the trough to the top in most situations. Okay, so that is the amplitude of a wave, okay? Graphically, you can see where that lies, and it also connects with the volume of the sound and the amount of energy that was put into creates that sound. Okay, so properties of sound amplitude. Like I was saying, we perceive sound as loud and quiet. We kind of interpret these in our human way by perceiving sound as being loud and quiet, but the way that we measure that human perception is with a term called decibels. The abbreviation is a lowercase d, uppercase B. Also the spelling of decibels But essentially, the idea with decibels is it's not perfectly equal to the volume. Just because you put it's not perfectly equal to the energy. We'll say that. So just because you put twice as much energy into a sound doesn't mean it's going to be twice as loud to a listener. So it's not a total equal comparison, because humans and our perception is not perfectly aligned with the measurement of energy. Okay, so I won't go into detail about all that, but essentially know that volume is how we perceive sound, and we measure that in decibels. That's what you're going to see in most audio situations with, amplification and with DAWs and manipulating sound and turning things up on the faders. That's not a direct equivalent to energy, but energy is causing things to be louder in volume, just not in the same equal way that we perceive it. So anyway, hopefully you're not too confused. I'm sure you are, but there's basically a graphical representation of energy to decibels, and it's more of a curved thing. It's an exponential curve, so that it's not perfectly equal. Like twice as much volume does not equal, or twice as much energy does not essentially equal twice as much human perceived volume. Okay, so onward with frequency measurements. So frequency is analogous, or it's kind of equal to pitch, the highness and lowness of a note. High pitches on the piano, low pitches on the piano. These are different frequencies, okay? And frequency is how quickly a wave will cycle from the positive to the negative and back to the center. Okay, so positive run, negative run, and then coming back to the center point. That's what we call one cycle of a wave. And frequency is essentially the amount of cycles per second. How many times the wave will cycle up and down in a second. Sometimes that happens a lot. With the high frequency, high pitch sound, that cycle is going to happen very quickly. Very quickly is cycling. Where a low frequency sound takes a little bit longer. And we measure that with a unit of measurement called hertz, abbreviated with capital H and a lowercase z. It was dreamt up or created by a German scientist from the 1800s. But essentially we use hertz to quantify the pitch and frequencies, high frequency, low frequencies of sounds. Sometimes we use kilohertz because you'll get into the tens of thousands of cycles per second, and we'll use like kilohertz instead of 10,000 hertz. We'll use 10 kilohertz. So that's what we see when we deal with audio in most digital situations and analog situations with audio technology. Okay, so this is more on the pitch and how that relates to wavelength. So obviously, if we have a wave that cycles very quickly, it's like super fast, the length of the wave, the physical length of the wave is going to be shorter than a wave that's a low frequency and does a very low, slow, gradual cycle. There'll be a lot much more distance it takes for that wave to physically go up and down and then back to the center crossing to complete one cycle. So you can kind of see that down here. So wavelength is pretty connected to the frequency. Okay. This is another representation of wavelength. It's kind of the distance, like I said, of one cycle. It's a physical distance of that one cycle, where the other one is how many cycles happen per second, so it's related to time. And that brings us to an equation that basically shows us the relationship between frequency, between wavelength, and the constant, which is the sound, the speed of sound. Okay, so lambda being the wavelength, the physical distance, equals the velocity of sound, which is a constant, divided by the frequency. Okay, so it's just the correlation between these three aspects. They're all related, but really it's not so much this is in a math class, but you want to know that low frequencies have a longer wavelength, which is how they're physically reacting and manifesting themselves in the space, which might which might, factor into how you might choose to record these sounds and issues that happen. Certain rooms have a certain sound about them. Some rooms boost low frequencies, some rooms bring out high frequencies. And when you're listening to music in a certain environment or recording it in a certain environment, having some awareness of the sound and its wavelength can help you understand why certain sounds are boomier or less prevalent in a room, and that's because of the wavelength. If it's a certain length of a wave, and it just so happens that this room is 15 feet long, and the wavelength of that frequency is 15 feet long, that wave is going to nicely form one cycle. It's going to hit the wall, it's going to bounce back, and maybe come back on itself in the opposite direction, canceling the wave's sound and making that sound quieter in this room. Or it might double itself up and make that sound twice as loud. That's why a lot of times if you put your ear in the corner of a room while someone's playing music, you'll hear these low frequencies, because the low frequencies kind of get collected in the corners. So anyway, these things come into, they factor into the tones of rooms and how certain frequencies might need to be cut or boosted to make a room sound more even and make a room sound, more even for mastering and mixing and listening critically to sound. Okay, moving on. Another aspect of sound in the waveform is timbre. Timbre is a musical term for the tone or the color of a sound. This is a very complex thing. It's made up of, there's a lot of messiness to real life instruments, like a voice, a guitar, a violin, some kind of instrument in the real life setting is a very messy frequency. It's a very messy waveform. It's not a perfect smooth wave like we were looking at earlier. It's not a sine wave. That's something that a synthesizer can create. But in real life, sounds are very messy. They're all crazy and jagged, and they're all bumpy and going left. They're going positive, negative, and cycling, but they're doing it in a very messy way. If you've ever zoomed into the waveform in a DAW, like Pro Tools or something, you look closely and you can see how jagged these little waves are. They're not smooth. So that jaggedness is kind of the tone of the sound. Okay, a term we call timbre, and that's how we can tell instruments apart. Like we can tell a trumpet that plays a same note as a violin, that plays the same note as a voice, that plays the same note as a piano or something. All those are the same pitches, the same frequency, but they sound very, very different because they have different timbres. Okay? So, let's talk about how waves behave. This is very important. Like, it's good to know that low frequencies have long waveforms, long wavelengths, while small high-pitched frequencies have short wavelengths. They're going to react in spaces physically based on those shapes and those waveforms. So, reflection. Sound reflects. If I talk against a flat wall, that sound is going to ricochet directly back at me. Okay, so if I'm in a recording studio or I'm listening to music on speakers, I don't want my speakers to face a flat wall because that sound is going to echo and ricochet back. It's going to reflect back. So sound bounces off and reflects, much like in pool. When you shoot a ball in a pool table and it hits a bumper, it's going to reflect equal and opposite and kind of come back at you the opposite direction. So sound does the exact same thing, and that's reflection. Diffraction is basically when sound moves around an obstacle. I might talk directly into my phone here, but you can still hear my voice. It might sound a little bit different than it sounds right here, but this sound and the sound is going to work its way around and diffract around that object and work its way around. It does that in rooms. You can hear sound creep through doorways and through window cracks and through vents in the air duct work in a house or something. Those little spaces, sound will diffract itself and weasel itself through little cracks and stuff like that quite often. So that's diffraction. Absorption is another way that sounds behave and interact with objects. That is one of the key ways that we use to kind of control all this reflection and all this diffraction is to put up things like that acoustic panel you see behind me that is made out of like burlap that's wrapped around really dense acoustic foam, acoustic insulation with a high coefficient of acoustic absorption. And I put these things all over my walls and ceilings and stuff in this room so that it doesn't sound like I'm in a bedroom in a box. The sound will reflect everywhere. I got hardwood floors here, so it'd just be a messy, live sounding room with a lot of reverberation, a lot of frequencies bouncing off of every direction and all the walls, and just a big messy sound. I tighten this room up by putting baffles and sound absorption all over the place to make the room a little bit quieter, a little bit more focused. And that's a lot of times what people do in recording studios to make the room sound a little bit tighter and less live. Sometimes you want a live room because you want to get that natural acoustic sound. Sometimes you want a tight, dead room because you want to add a reverb later. But absorption is the key to controlling these frequencies and how they bounce around a lot. Retransmission is the fourth kind here, and that's when sounds basically go into an object and they vibrate that material and then they exit that material. I can maybe do that with a piece of paper. Hey, Macarena. Like, whatever, I'm talking into a piece of paper. You can hear the vibration of the paper. That vibration now gets out of the material and goes out into the room and retransmits itself on the other side. This happens with walls. You play music in one room of the house, you can hear it in the other room of the house, mostly because it's vibrating the wall, and then the wall continues to exit the sound. It exits on the other side of the wall and continues into the air. So retransmission happens a lot with a guitar. That's how a guitar works. You play a guitar string, it vibrates the whole wood body. So the entire vibrating wood body of the guitar is retransmitting that vibration into the air around it. And that's why an acoustic guitar sounds louder than an electric guitar, because it's got a big wood body. All the air inside and all the wood retransmits that sound outside into the space. So in a space, when you're talking or playing music in a room, there's sound of all frequencies going in every chaotic direction. It's a lot like a lake on a busy summer day where there's boats and jet skis and people wakeboarding and whatever, running around the lake doing stuff. There's lots of chop, lots of waves bouncing everywhere. It's all moving, it's propagating and reflecting off of the surfaces and other waves interacting. It's a big, messy, choppy chaos environment. And that is a lot of times what goes on in a room that has a lot of hard surfaces. Everything bounces around, like in a restaurant where there's nothing but hard surfaces. It's loud, it's obnoxious, it hurts your hearing, hurts your ears, because there's no absorption and everything is just bouncing around like nuts. So good to know these things, because physics and these sound waves and how these things physically happen, they also dictate the way things sound. And the more aware you are of those things, the more you can make your room sound better, you make your recording sound better by being aware of these things and the behaviors of sound waves. Okay, a little bit more about reflection of sound. I mentioned earlier that it's equal and opposite. Things bounce off of surfaces and continue at the equal opposite angle. Incident sound is the direct source. So like my voice is the incident sound that you guys are hearing. The reflective sound is maybe some of the room characteristics. Like if I turn around, hey, blah, 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 blah. You're hearing a lot of reflected sound. The sound is hitting that corner of the room, bouncing back, and the microphone sitting in front of me is picking that sound up as it reflects off the wall. That's why it sounds differently if I talk here. It sounds differently if I talk here, right? That's all because of these physical principles that we're talking about. Diffraction is kind of similar to like diffusion, where sound can it can basically sneak through little cracks in the walls or the doors, and it can reform itself on the outside of that place. So this happens a lot with low frequencies. I don't know if you guys have ever heard a car coming down the block that has like the bass cranked, and you hear the bass first. Bass frequencies are very long wavelengths, very snaky, slow waveforms that can easily sneak under a doorway, sneak through a window, and retransmit itself on the other side and reconstruct itself. And that's why bass frequencies are the hardest to deal with. You're going to hear the bass that's coming out of your neighbor's speaker more than the high frequencies, because high frequencies get all caught up and diffused and where low frequencies can diffract themselves and reform and basically sneak through things. So yeah, it's always tough to deal with the low frequencies. They're very sneaky because of those waveforms, and they can sneak through cracks and stuff like that. So that's why that is. All right, another really important aspect of sound and waves and physics and stuff is the phase relationship. So when you have two microphones on one sound, like an acoustic guitar with two microphones recording it, these two microphones are both picking up the sound. They're recording the waveforms of the sound. And depending on the distance of those mics, whether they're perfectly even or one's a little bit further away, the waveforms will be a little offset. Okay? Another situation is when you have a snare drum or a kick drum. You have a microphone on the front and a microphone on the back of that drum. They're in opposite directions of each other. They're picking up the same sound, but one's going to hear it in an opposite polarity. It's going to be totally out of phase of the other one. And that's kind of what you're looking at in this diagram. You can see maybe this is the kick drum of the front microphone, and then this is the back side of the kick drum microphone. They're totally opposite phase, which means the positive and negative traveling of the wave is moving in opposite directions, right? Now that is an issue because these waves are energy. If you have positive energy with negative energy happening in the same exact time in the opposite direction, they cancel each other out. So that's an issue when you have two microphones on one source. For instance, this diagram kind of shows what happens with two microphones on a snare drum or a kick drum in opposite directions. Over here we have the 180 degree out of phase. They can cancel each other out. +1 plus -1 equals 0. So you need to switch those waveforms, flip them around with a phase switch, which you can find on a lot of plugins, or you can find them on mixing boards where you know that two microphones facing the opposite direction on a kick drum are always going to be out of phase. So you have to flip the polarity on one so that it's going positive, traveling positive at the same instant, much like we see on this in phase example. Positive movement in phase, that's going to equal twice as much volume. All right, so be aware of that when you layer kick drum samples or something like that, and you have two kick drums kicking at once going positive, that's going to be twice as, well, not twice as loud because we don't perceive things in that same way, but twice as much energy. A little bit louder of a kick drum. You might need to turn that kick drum now down because there's two kick drums playing at once, thus twice as much energy. But yeah, a lot of times waves are a little bit messier. So in the situation of a guitar with two microphones on it, these things might be slightly off of phase, slightly phase shifted. So two waves, one might be just a little bit sooner than the other. And this happens a lot of times, like, two microphones on one source, and the distance between those microphones might be slightly off, and that creates phasing. Sounds a little weird, a little phasey, a little bit not crisp and clean. So we zoom into the DAW waveforms and we correct these things a lot of times by scooting waveforms to line up more perfectly. We're talking like milliseconds here. Very, very hard to see. You have to zoom way into your waveform to kind of see this happen. But these types of things happen all the time, and this is something that an engineer, a mixing engineer, mastering engineer, more so mixing engineer, will deal with and look at to make sure that all these sounds are kind of in phase with one another. Everything's got to be lined up and going positive at the same time. Not going to be off a little bit unless you purposefully do that. But yeah, phasing can give kind of a weird stereophonic sound, which might be cool in certain situations. You might do this purposefully and pan two guitars apart out of phase so that they sound wide. But sometimes you want that guitar to be focused, or that voice to be focused, or that kick drum to be focused. So you want to arrange all those waveforms to be perfectly lined up. So that's kind of phasing. It's a big deal, something you always got to be aware of. All right, so we'll skip over this waveform stuff. This is more synthesizer thingies. One thing I do want to mention here is this idea of harmonic content. So real life instruments like voices and guitars and basses and drums and things in the real natural environment, they're not perfect sine waves. That this little wave that we've been looking at, this little sine wave, this does not exist in nature. This is what you can create with a sine wave oscillator on a synthesizer, but this is not real life sounds. Like this is it's like robot sounds right here. It's a clean, perfect pitch, but it's not something we see in real life. We see these messier versions of this where it's like it's just like all jagged looking. It travels positive and negative, but it's all shaky and jagged because there's all these other levels of frequencies, these overtones or this harmonic content that is going above the initial tone. There might be a middle C happening on the guitar, but it's going to have several layers of upper frequencies and things that are more subtle but give it that real life depth. Okay? We create those with synthesizers, and we have layers and layers and layers of oscillators that are pitched in different partials and overtones and detuned, and we get more of like a multi-dimensional sound, by creating these with synthesizers. But these are also active in many instruments naturally. So these upper partials, these overtones are just layers of other frequencies that are coming along for the ride. There's a fundamental pitch. Oh, it's C. That's a C I'm singing or playing on the guitar. But there's also levels of other frequencies that are kind of above that exist, and that's the messiness of real life acoustic sounds. They're not perfect. So harmonics or overtones are kind of terms we use sometimes for those upper, extra frequencies that give it that, that depth and that multi-dimensional sound. All right, cool. Now, another really important key feature of an aspect of sound is the envelope. Okay, and that's like this the visual shape of a sound, really. Not so much physical, but along with timbre, like the tone of a sound. I can hear a trumpet, I can hear a violin. They sound different. Same note, but I can tell them apart. Partly that's the overtones and all the timbre of that frequency and all the different messiness of it, all the layers and all the depth and all the overtones. But it's also a part of the envelope, the shape of that sound. Okay, so we kind of quantify all that stuff with a graph, or kind of like this. This is a sound envelope, and we break it apart into 4 little pieces. We have the attack, which is the initial instant ramp up of the sound, or gradual ramp up of the sound. Then the sound starts to sort of die pretty instantly after it reaches its peak volume. It starts to die. It might resonate and sustain for a little bit of time, right? Ring out in the room. And then eventually that sound will stop. Okay? So depending on the instrument, these instruments all have different shapes of envelopes. A trumpet sounds different from a violin, sounds different from a guitar. Yes, because the timbre is different, but also because of the shape of the envelope. A guitar is plucked, so the sound instantly goes all the way up in volume. Ba! And then it dies. It goes up quickly, it starts to decay real quick, and then it maybe sustains and rings for a little bit, and then eventually the note ends. You can touch the string and stop the note, and there will be a very quick release. Or the note might just slowly die, and then at the very end it's like, ah. And that was a little bit longer of a release. So these 4 aspects, attack, decay, sustain, release, these are the elements, the aspects, parts of a sound envelope. You'll see this stuff all the time. You're going to see it with synthesizers when you create synthesizers and you're shaping the waveform. You'll see these in the DAW when you see the shape of a sound in its waveform, its visual thing. A snare drum and a kick drum and a guitar and a hi-hat and a voice are going to have different shaped envelopes on all of the sound of the waveforms. And you're going to see the attack and the decay and the sustain and release and how those are, variety of those in those shapes. But one way of remembering this is ADSR. It's a mnemonic phrase, ADSR, the order, attack, decay, sustain, release, ADSR. Okay? So, that kind of just explains what I was talking about a little bit more. The attack is the manner at which the sound begins and increases in intensity. The internal dynamics, basically the slowly dying of the sound, it decays, it sustains, and then at the end you kind of cut it off. Do you cut it off with your finger? Do you cut the note off with your tongue or something when you're da? You can have a quick release, or you can go da, and that's more of a gradual release. It's like the cutoff. I think of release as the cutoff of a note. All right, cool. Visually, in the DAW, we see this kind of stuff. Here's a DAW. Here's like, a edit view of Pro Tools of a song. And you can see these different things. Oh, that might be the kick drum. That might be the snare. Maybe this is the cymbal or something. And here's, I don't know, the bass, or here's a voice. These sounds are going to visually represent the sound. Okay? And these three things here might be three different instruments. This might be a snare drum crack or a clap. Very quick attack, quick release, decay, and all that other stuff. Excuse me. This other thing might be a guitar plucking. This might be a plucked guitar sound where very quick attack, slower decays, gradual release. The note kind of rings out for a while before it dies. This might be a voice or a violin, something that has a slow attack. Slowly ramps up, unlike a plucked note that goes ta, quick attack, slow attack. So anyway, you can recreate these with instruments and your voice. Hopefully that makes sense. But envelope is a very, very important aspect of sound. Visually identifying it and the way it sounds, telling different instruments apart, as well as when you're working with synthesizers and you're creating your own sounds, you are using attack and release and decay times to shape the sound and create a synth sound that sounds like a brass instrument or a plucked string instrument. Okay? All right, cool. Electrical representation of sound. This is a really good topic because it's kind of starting to get into microphones and how microphones work. So essentially, like we've been talking about, acoustic sound is vibrating air particles, compression, rarefaction, spreading apart and smashing together. We document that and kind of analyze that and look at that visually with a sine wave. But the way that we record and document sound when we record it is with electrical energy. We basically collect the movement and convert it to electrical alternating current. Okay, so the way that works with a microphone. This here is a condenser microphone. It has a little disc, a metallic disc in the middle, and that little metallic disc has another disc right behind it, and those two metallic discs are very thin, and they're like about like a micron, a micrometer. They're just very, 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 very close together, but separate. And then there's electrical charge traveling. There's electricity traveling across those two plates from one plate to the other, right? So there's this little distance between the two, and then a difference in charge. When you talk into this thing, hello, hello, they vibrate, and that distance changes, thus making the voltage change. So we have a plus minus representation of the sound wave converted to electricity in an alternating current. Same thing with a microphone that's like a dynamic microphone. They do that with magnets. There's a little disc that vibrates, and then it's sitting in between a coil. It's got a coil on it, and there's some magnets on either side. And as that coil vibrates and moves between the magnets, the two plus and minus wires on the end of that those magnets, there's a slight variation in the plus and minus voltage. That's what travels through the mic cable into the speaker, into the recording interface. If it's a recording interface, those little fluctuations of electricity are converted to ones and zeros and then get digitized, go through the computer. After the computer processes that, it comes back into the interface. The interface converts it into electrical energy. It sends it into a speaker. That speaker cone pushes air by vibrating, and that turns it back into acoustic energy, into sound pressure levels. So microphones are basically like the opposite of speakers. Electric guitar is another example of this. We have an electric guitar. It's got a string. It's made out of steel. You play the string, it vibrates. How does it turn that into super loud rock and roll guitar? There's a magnet underneath, a pickup underneath that string. And when it vibrates, that magnetic field in the plus and minus wire is disturbed, and we have an alternating current forming based on the pitch and the frequency of that string vibrating. That little electrical signal is sent through the cable into the amplifier. The amplifier cranks it up the volume and puts electricity and way more energy behind it. It pushes it into a speaker with a big, powerful, powered magnet that pushes the cone in and out real quickly, thus vibrating the air particles, making that sound acoustic air sound, sound pressure levels, as it's called. So this is kind of the basics and physics that we rely on with recording sound and amplifying sound for PA systems, live sound, or in engineering and recording, mixing and mastering. It's all that stuff going from analog to digital and back out again. So we use alternating current to sort of document the vibrating air particles. Okay, cool. So a frequency response curve, since we're in microphones a little bit, we'll kind of continue to kind of talk about how microphones work a touch. But all microphones have like a unique frequency response or a unique tone. Some microphones sound dark. Some microphones sound bright. Okay, and that's because they have a different frequency response. So the audible frequency that humans can hear is from 20 hertz to 20,000 hertz, or 20K, or 20 kilohertz. That's usually how you say it. But anyway, we can only hear this narrow range of frequencies. There's frequencies that go beyond that. We just can't see them or we can't hear them. So anyway, that's what we document music with, right? We have 20 to 20,000 hertz. That's what we can hear. That's what comes out of our speakers. That's what we deal with when we mix and master and sort of, digitally mess around with music. Now, microphones have a unique response. They're not perfectly flat, meaning like this SM57 microphone will pick up a little bit more in the upper mids than it does in the mids, right? It's going to boost a little bit around whatever this frequency is. Maybe that's 4K or something. But it's got a little boost up there, and then it rolls off around the very, very highs. It's pretty flat in the middle, and then it rolls off in the low end. So not super great for low frequencies. Other microphones might be better, but this is the tone of the microphone. This is the frequency response. And when you purchase a microphone, when you use a microphone, this can give you some clue on how it's going to sound. Do you want a dark sound? Do you want a bright sound? Do you want it to be darker or brighter? You can EQ that sound by using a certain type of microphone that captures more highs or more lows to basically, document that. Another thing about this, these curves or these diagrams that come with the microphone is the polar pattern. And this is kind of like how the microphone in a three-dimensional environment picks up sound. So most microphones, especially a dynamic microphone like an SM57, it has a what's called a cardioid polar pattern, which means it's going to pick up sound from the front of the microphone. As you go around the side of the microphone, it starts getting a little bit less, and then from the back of the microphone, you can't hear much anything. That's kind of what's going on. This 0-degree axis is the front of the microphone. Like I'm talking right into the front of this microphone, okay? As I rotate the microphone and keep talking, you're going to start to hear the sound get a little bit quieter, and when I'm on the back, you'll probably just hear the reflected sound off my monitor in front of me. But essentially, it's going to pick up sound the best from the front, not so great from the sides, and maybe nothing from the back. So this is logistical orientation of the microphone, and you might put it a certain way and put it in front of a thing in a certain way so that it doesn't pick up sound from the back, or maybe ignores a sound that's coming from another instrument that's behind it. So you strategically kind of place these things and utilize your understanding of the frequency response, the tone, as well as how the microphone reacts to sounds coming into it from the front, the sides, the back. Some microphones pick up sound from front and back and nothing in the sides. Some pick up things like all the way around 360, omnidirectional. So we'll dive into this a little bit more in another video. But anyway, that's a little bit about frequencies, or about sound acoustics, sound and hearing, how we perceive sounds, how sounds are quantified, how they're documented and transferred from, moving air particles to electricity and then into the DAW. It's all just kind of these scientific terms. And also, it directly affects the way things sound. If you're going to set up a recording studio or record music in a certain room, you might use your understanding of the physics of different instruments to dampen sound and keep it from reflecting and bouncing around, because that changes the sound of the guitar. It sounds like it's in a bathroom. It sounds like it's in a hallway. It sounds like it's just super quiet in front of your face. Like, all that's based on the reflection of sound in a certain space, which changes the characteristics of it. So all these things are at play all the time, no matter if you're an acoustic instrumentalist or a recording engineer or an EDM artist. You are dealing with frequencies and sound envelopes and sound bouncing around spaces and all that stuff. So the more you understand about this stuff and the more you have a grasp of it, the better you can make decisions and the better sounds you can create that are more purposeful and more along what you're trying to get to musically. So hopefully you got something out of this video. Take care. We'll see you in the next one. Peace out.